This is Chapter 2, Lecture 2A. In this chapter, we'll be talking about forces, vectors, and how to add them together and in general manipulate them. Recall that a force is represented by a push or a pull or the action of one body on another. A force, by definition, has a point of application, a magnitude, and a direction. We represent a force as a vector, and hence vectors also have the same application, magnitude, and direction. In this simple example, we have a 10-pound force whose point of application is at point A, that is at a 30-degree angle above the horizontal and has a magnitude of 10 pounds. In B, we have essentially the same force, only in the opposite direction. So the direction of the vector is sometimes referred to as its sense, where it's going. The line of action can be considered an infinite line along which the vector acts. Now, because forces are vectors, they can be added. And we add them in a similar fashion, regardless of whether we're adding 1, 2, or 10 vectors. Let's just start out with just look at two simple vectors. We have vectors P and Q, and typically what you'll do is you'll pick one vector and you'll attach that to the tip of the other vector. So in this example, if we were to put the tail of Q at the tip of P, we would get the dotted line. Or if we were to put the tip of, the tail of P to the tip of Q, we would also get the dotted line. This would equate to this P plus Q, which is hence our resultant vector. This is sometimes referred to as the parallelogram method or the tip to tail method. Something I'm sure you're familiar with from your math classes. And as such, drawing these schematically on paper is not difficult, but to get an accurate addition is not so easy. So whether we use the tip to tail method or the parallelogram method, it doesn't matter which vector you start with. If you have multiple forces, more than two, then you start off with adding two of those forces together and then finding the resultant. So here we have P plus Q gives us the resultant in the blue arrow. And then we go ahead and we add S, which gives us P plus Q plus S. And again, it doesn't matter which order you add them in, the result will always be the same. If you had more than three vectors, you could continue to just add as you saw fit until you had the resultant for all of your vectors. So again, doesn't matter how you start. So for most of you, this should be review, fairly simple concept, just something where we want to be sure that we're all on the same page as we move forward. Now, part of the reason I go over this material is that Chapter 2 will build on it. Chapter 2 is used to understand the material in Chapter 3, 4, 5, and so forth. And so you need to have that strong foundation starting now if you're going to do well in the subsequent chapters. Now, for subtracting vectors, it's the same as adding a negative. Also, if you want to increase the size of a vector, they can be multiplied by a scalar value. So here we have an example of P. We have 1.5 times P, which is just a 1.5 times length of vector. Or if we have negative 2P, it would be double the length, only in the opposite direction or opposite sense. So adding vectors is trivial looking at it from a schematic standpoint. We can draw the lines and we can add them. But if we really want to get accurate answers, it would be a fairly time-consuming process. We would need a protractor and a ruler. We would have to put some scale. We'd have to derive some scale for the amount of force. And we would have to be able to draw the vectors such that we could easily measure their final resultant and have some kind of final resultant value. This isn't as easy, and you may have done it in high school or before. It's a good exercise when you're first learning vectors, but at this point we can use other tools to get our answers. So my first example we're going to be adding two vectors. So we have P and Q using trigonometry. So P, 175 newtons, Q, 100 newtons at their respective angles. Now, before I jump into the example, I want to show you the law of cosine and the law of sines. Here we have, for the law of cosines, if we look at our typical triangle with sides A, B, and C, we have alpha, beta, gamma. A squared equals B squared plus C squared minus 2BC cosine alpha. This is the law of cosines. And so, depending on the side you're using, you can use this equation. This is a good equation if you know two of the sides and the included angle. Then there's also the law of sines, which says that if you have the angle that's opposite the side, that's going to be equal to the angle sine times the angle over the opposite side, which is equal to the other angle over its respective side. And lastly, just be sure you understand the relationships of tangent, cosine, and sine. Now here's our example. So as I wrote in the example, we have 175 newtons at 35 degrees. We have the 100 newtons at 50 degrees. And so we're going to find the resultant. Now we could, as I said, do it graphically. We could scale out each respective square equaling so many newtons, and we could get a protractor to get exactly 35 degrees. But an easier way to do it is just using the law of cosines. So first we're going to draw this. We have down here, we have our P. Now notice I've written P at the same angle as it is up here, 35 degrees, labeling it 35. And I have Q over here at 50 degrees. And adding Q to P allows me to find R. R then subsequently gets me my phi. Now, phi is simply the opposite angle of Q. So when we do this, we're going to find that side R using this included angle. So if we use our equation, we know we have 175 squared plus 100 squared minus 2 times 175 times 100 cosine 85. That gives me R. Now, R is 193.8 newtons. And so notice I had the sig figs here, but I went ahead and I rounded so that I had 193.8. Then I look at my directions. I've gotten the resultant, but now what I want to do is I want to know I want to know what the actual angle is. And so this angle here I can find from the law of sines. I know that Q over the sine of phi is going to be the same as R over the sine of this angle. And so here I have 100 newtons over sine of phi, 193.8 over the sine of 85. And that gives me phi equal to 30.9 degrees. So finally we have 193.8 newtons at 65.9. And I just got that by simply adding 30.9 to the 35 degrees. And that's our first example. Now we can look at our second example. So in this example, we're given that we have a 8 kilonewton force up to the right and a 6 kilonewton force down to the lower right. And we're trying to find this angle theta up in the corner such that our resultant is a horizontal line to the right. So here is that example written out. So here I have my theta, I have my 40 degrees, 8 kilonewtons, 6 kilonewtons. So I know I want to get R so that it's horizontal, and I want to find theta. So again, I just go ahead and I draw my R. I have my one angle, 8 kilonewtons coming up, the 6 kilonewtons coming down for my triangle. And then I go ahead and label what I can. I know that's R, I know that's 6 kilonewtons, 8 kilonewtons. I know this angle is alpha, this alpha is theta. I know by geometry that this angle up here also has to be theta. So first off, I use the law of sines to find what is this included angle alpha. Because if I know that, then I know that that theta plus alpha is going to be 90 degrees. So I go ahead and I solve for alpha, and I get 35.067 degrees, which gives me 90 minus 35.067, or a theta of 54.9 degrees. So that's part of our answer, a theta at 54.9 degrees, but we also want to know what the resultant is. Now, because we now know what this angle is, we can use the law of cosines because we have the included angle and the two side angles. Go ahead and plug it in. We get our result, 10.4 kilonewtons. So that's the answer to that problem. We have our resultant, we have our angle, and then we're done. Now we have problem 2 on our example worksheet. And so in this problem, we have, it's very similar to the ones we've done, but we start off with two forces, P and Q, that are connected at point A, and we have our respective angles showing. So let's go ahead and look at this problem. So here we have our forces, 60 newtons and 48 newtons. We want to find R. And so we go ahead, and this included angle from the geometry of the problem is 150. You can find it fairly easily. I'm not going to go over how to do it because it's simple geometry. But once you get that, you have your R value, and you can go ahead and plug it into the law of cosines. We plug that into law of cosines, get 104.4 newtons. And then we just want to know what our direction is, right? Because we want to know the magnitude of R and its direction. So come down here, want to find what I'm referring to as alpha, the included angle. And so I can do that by using the law of sine. I have the alpha's opposite force is 60 newtons. And then, of course, opposite of 104.4. So I have 104.4 sine 150 equals this, 60 newtons over sine alpha. Therefore, alpha is 16.71 degrees. So my final answer then becomes 104.4 newtons at 83.3 degrees if I look at the supplement, or it can be 104.4 newtons at 106.7 degrees. And either one's correct, doesn't matter what you do. So one thing to note is that on these lectures, I will have examples that I will post. And so I would go ahead and look at the examples for that particular lecture, and if you wish, print them out and have them ready. And the good thing about this is if there's something that you missed while I'm talking about it, feel free to pause the lecture, go back and look at it. And again, if you have any questions, by all means, come speak to me during office hours via Zoom. Thank you.